Hi there, welcome to your lesson on the definition of the derivative. Over here, this symbol means derivative. So we already know what a function is, and this is how we show the derivative of a function. Now what does the word derive mean? Or derivative comes from the word derive. Derive is defined as to obtain something from a specific source. So in this case, in mathematics, it's the same thing. When we take a derivative, the source is our original function, and we're taking the derivative of that function. And here we have this nice graphic here. From a cow, we get milk, so milk is derived from a cow, and then cheese is derived from that. So we have here what is called a double derivative. Okay, let's get started with derivatives. So first question, and this is what derivatives are all about. Derivatives are all about slope. So the question is, what is the slope of this graph? When we have a linear function, we know finding slope is easy. We just need the rise and the run, or the what's called the change in y over the change in x. To find out the slope from here to here, we just need to know how much it goes up, change in y, and how much it goes side to side, change in x. That's what these symbols mean here, change in y, change in x. We know the formula from that is y2 minus y1 over x2 minus x1. All right, on this function here, our values are 5 and 2 for y. So here is a y value of 5, here is a y value of 2. Therefore 5 minus 2 gives us this rise. And then on the bottom, 3 and 1, we have an x value of 3 here and an x value of 1 here. So the difference here is 3 minus 1, which is 2. So we have just found out the slope is 3 over 2. Because the rise, it rises 3 and it runs 2. 3 over 2. Okay, this is a simple idea, but it's essential to understanding derivatives. So let's look at this graph now. Now this is a curve. And if I asked you what is the slope of this curve, what would you say? Okay, let's think of slope this way. There are many points along this curve. And when we go back to this line, no matter where you say I'm looking for the slope, like if I'm looking for the slope between these points or maybe two other points on this line or one point here and one point here, no matter where I check the slope, it's always the same because the slope is constant. But here, the slope of this curve is not constant. It's always changing. So for example, at this point right here, that would be your slope. This is called a tangent line. A tangent line is a line that hits a curve at only one point. So when we draw a tangent line at that point, we're basically saying, well, at that moment in time, at that point, that is the slope of this curve at that moment. The slope depends on your location. For example, if we move to another location right here, it has a different slope. So at that location on the curve, the slope would be determined by this tangent line. And now if we move further along the curve, we could be here. We're near the bottom of this dip here, but the slope is slightly downwards. At the very bottom point, the minimum point, there would be a flat line, no slope, but we can see there's a little bit of downward slope here. And one more point, let's say we went over here, tangent line looks like this, so we could say the slope at that point is that. So the slope of a curve changes as you follow the curve, but the slope at each location can be determined by drawing a tangent line and finding the slope of that tangent line. Let's go further with this, because this is the big idea in the heart of derivatives. So again, the derivative is the slope of a tangent line. Okay, the derivative is the slope of a tangent line. So if you have a curve and you draw a tangent, the derivative is that slope. Let's look at this online. So in here in Desmos, I have this curve and I have a slider here. When I move the slider, it's going to move this location. So as the location changes, we're going to see a different tangent line or a different slope at that location. See, notice, first the function is very steep, and we can see the tangent lines show us that. Very big slope, very big positive slope, right? But then as you follow the curve, the tangent lines are less steep. There's not as much slope, not as much. And when you get to the top, I don't think it's going to show it because I don't have the right A values. But if you were right at the top, it would be horizontal, no slope. And then it's a downward slope, downward slope. So tangent lines always show us the slope. Okay. And the derivative will give us the equation of the tangent lines. Okay, so let's take a look at that now. Okay, so again, here's the tangent line, and we can see at this point that's the tangent line. Therefore, the slope at that point is the slope of this tangent line. Here is a tangent line again, but also a secant line. So secant line means it intersects the curve at 2 points. A tangent line intersects at 1 point. So again, that's just to show the difference there. Because when we figure out what a derivative is, we're going to begin with a secant line, and we're going to turn it into a tangent line. So here's that idea shown here. as this red point moves out right here, we have a red line, a secant line. But as the red point comes closer to this point, we end up having a tangent line. So just watch this for a moment again. Here's our secant line, and as it gets closer, it becomes like the tangent line. So the closer we can get one point to another point on a line or on a curve, the better we can figure out what the slope is at that moment. Because here, if we found the slope, we'd have a different slope. Here, if we found the slope, we'd have something very close to the actual slope. So that's our goal with derivatives. Move one point closer to another so that we create a tangent line instead of a secant line, because we know how to find the slope of a secant, but how about at one point? So let's try this concept out. Okay, let's take some notes. We're going to draw this diagram twice. One time is going to have numbers here. A second time there's not going to be numbers here. So we're going to go from a concrete example to an abstract example. And this is the heart of a derivative right here in this diagram and what we're going to discuss. So let's take careful notes. So first of all, we are given these 2 points and we're going to find the slope of the secant line from P to Q. So connecting those 2 points, we're going to find that slope right there. So the slope can be represented by that connecting line, and then we can draw a slope triangle because we're going to get the rise and the run and find the slope. Okay, let's fill in some blanks. First of all, we know this x value is 2. We know there's a distance of 4 here. So what's this x value? Well, I hope you're thinking clearly that must be 6 because it goes up by 4. Okay, now that we know this location, we can label our 2 coordinates. Let's start with coordinate P. What is the location of point P? Well, the coordinates are 2, x, and 1 on the y, so 2, 1. What about point Q? What are the coordinates of Q? Well, that one has coordinates 6, 7. All right, now that we have the coordinates of our 2 points, we can find the slope of this secant line connecting them. So find the slope using the slope formula. Okay, here's our slope formula. The slope of PQ is change in y, delta y over delta x. And that is 7 minus 1 over 6 minus 2 gives us a slope of 6 over 4, which is 3 over 2. So that's a basic slope problem, but we're going to use this idea now to move on to derivatives. So draw this diagram again, but make it look like this. Instead of numbers here, we have nothing. We just have x here and h here. So let's try this again. Take a moment to draw it now. We're looking for the slope from P to Q, so we draw our slope line here, our secant, and we have our triangle to show the slope. Now, if this is x and this distance is h, what is the location of this value here? Well, that must be x plus h, because we went from x, we added h to it. Just like if we had numbers 2 and 4, we added those numbers to get the new location, x plus h. Okay, next, what is the location of this coordinate here? We don't have a numerical value, but what is it? If we have a certain x value and this function of f of x, then what is the y value here? Well, the y value is f of x, right? Because you take whatever value you have here, let's say it was 3, put 3 into the function, and you'll figure out the y value. So f of x, because that's x. Okay, so what does that tell you about this location then? What is the input into the function that gives you this location? All right, I hope you came up with f of x plus h, because now this is the x value here. X plus h is this value. So you put that into the function, and you get f of x plus h, that y value. So now what is this coordinate here? What are the x and y values for this coordinate? Well, it's x comma f of x. It's the x value comma the y value. That's the location. What's the location of this point? This one is at x plus h, which is the x value, and then the y value is f of x plus h. So it looks kind of abstract, but I hope the way we did it step by step makes it clear how it works. Okay, now that we have defined our points P and Q and their locations, their coordinates, we can find the slope between P and Q. In the last part, we did the slope using numerical values, but we can do the slope using these abstract representations as well. So let's get the slope. The slope begins with the slope formula, y2 minus y1 over x2 minus x1. So the slope of PQ, the secant line, is here. We have y2 minus y1. Here's y2, here's y1. You subtract those to get this rise number. And on the bottom we have x2 minus x1. This number minus this number to get the run value. So this is just the slope formula. This can be simplified, however, because we see x plus h minus x. So the two x's on the bottom can cancel and we're left with just x. So now make sure you've written all this down, and this here represents the slope of the secant line from P to Q. The question is, we don't want the slope of the secant line. We know how to do the slope formula. How do we find the slope at point P? So in other words, remember the slope at point P would be the slope of this tangent line. What can we do with point Q to help us get this slope instead of this green one here from P to Q? All right, I hope you said that we can move Q closer to P along the curve, because as Q gets closer to P and we create the little slope between P and Q, it gets closer to representing this slope, which is the slope exactly at point P. So this is what this animation shows. We have point Q. I'm going to wait for it to come back. Point Q is over here. The red line represents the slope between P and Q, the secant slope. All right, as Q moves closer to P, so it's going to move there, the red line becomes like the orange line, which is the slope of the tangent line at point P. So as we get point Q closer to P, our secant slope becomes a better approximation of the tangent slope, and that's what derivatives are all about. So my last question for you is then, what is happening here? To find the slope at point P here, we can find the slope of PQ, okay, the slope of PQ. However, what are we doing to H? What is H approaching? And remember, H represents this gap between this x value and this one. Well, I hope you thought H is approaching 0, because as point Q moves towards point P, this gap, I gotta go back, this gap becomes 0. So we're setting a limit for H to become 0, and that means we're coming close here and creating the tangent slope. So that is our definition of a derivative. This is what derivatives are all about right here. This is the work we've done so far. This is the slope of the secant line. However, the derivative is the slope of a tangent line to a curve, so again we need the slope of this line here at that point. To find that slope, we set the limit as H approaches 0, this gap becomes 0, of the slope of PQ. So we're going to find the slope of PQ, but we're going to make the gap really tiny between P and Q. And that is our derivative, and that is the slope of the tangent line right there. Derivatives are represented with this notation. This says f primed of x, which means the derivative of function x, function f of x, or sometimes you'll see dy dx, and this just means delta y over delta x. That means change in y over change in x. It's a slope. Derivative is like a slope. Now let's apply this definition of a derivative to find the derivatives of some functions, and we're going to begin with the function f of x equals x squared. Here's the definition of a derivative again. So the derivative of this function will be found using this limit. Okay, first of all, when you see f of x plus h, that means you just take x plus h, you put it into your function, and in that case you get x plus h squared. When x plus h goes in there, this is what you get. So this part here becomes this. F of x, this says minus f of x, it just means minus the function, so minus x squared over h. So take a look, pause at any time and check your work carefully. Now we have this, we're going to expand these brackets to get this. Notice now we can cancel x squared and x squared here. We get this. Now we know with limits sometimes when you substitute the limit value into the expression, you will get something that's undefined. In this case, if we put 0 in here, we have 0 in the denominator. That's no good. So I look at this and I look for things I can cancel. I see h, 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 I can cancel. So I'm going to factor out the h on top and then cancel those h's, and I'm left with a simpler limit like this. Now I can substitute the 0 in there and get a value for that. What is it? What happens when you put 0 in there? What do you get? Well, we get 2x, and 2x is our derivative then. Notice the limit is gone, we're left with just the derivative is 2x. So there's your function, there is its derivative. Try the same process for x cubed. Begin with the definition of a derivative, the limit, and see if you can simplify it. This is going to be tough algebraically. You might not get it, but take a look carefully at the work when we're done so you can compare your work. So begin with the definition, check your work here, pause if you need to, check it very carefully. There's a lot happening here. And last one, try this one as well. We have this function. Try the definition to find the derivative of this function as well. Begin with that. Check your work carefully. There's also a lot happening here. This is a lot of algebra, but you can do it. So see if you can expand and check all your work carefully, cancel things, and you're left with this derivative. Now let's look at this one. We began by saying derivative is a slope, so let's check. Here's our function, here's the derivative we just found. Let's say I want to find the derivative, or the slope at x equals negative 1. So I take my derivative function, I put negative 1 into the derivative, and I get a slope value. Guess what? that is the slope at that point if you found it right